Hey Physics 20s, welcome back to another video. Today's going to be pretty short. We're going to go over work and energy, same as you covered it in Science 10, so a lot of it should be reviewed. This is just a little refresher to kind of recharge your brain cells a little bit. So just getting some definitions out of the way. Definition physics-wise of energy is the ability to do work. Now, it's not the best to use to define a word and then use another word in there, which we then need to define. So work and energy are concepts which are really very closely related. Work is a transfer of energy from one object or system to another, or a conversion of energy from one form to another. So energy conversions is kind of where we're going to go with it later on. But for now, we're going to first start off by defining it and doing some word problems and just sort of refreshing our Science 10 brain cells. So there's a formula on the screen there. Work equals force times distance times the cosine of theta. Now in Science 10, we didn't mess around with angles or anything like that. We didn't talk about vectors or components like we do in 20. If you recall in Science 10, work was just equal to force times distance. Well, now we're going to deal with situations where you've got forces happening at an angle. So for example, there's a student there pushing a box across the floor, and they're actually pushing down and forward at the same time. Same thing with, I don't know, let's say you're pulling a kid on a wagon or something like that. We can make an example like that where the handle is at an angle and you're pulling at an angle. So you're pulling forward and up. Or you're pushing on a snow shovel or something like that. You're shoveling the driveway where the handle of the snow shovel makes an angle. So you're pushing down and forward. However, in this case, the box, student pushing it, only has a horizontal displacement. It doesn't actually move in the direction of the force. It doesn't move into the ground. So only the component of the force that is parallel to the displacement, in this case horizontal, does the work. So we throw in that cos theta term to use the component that is parallel to the displacement. So we take a look at the diagram here. The force is actually down towards the ground and forward at some angle theta. It doesn't matter what it is. So it's got two components, one that's parallel to the displacement, horizontal, and the other that's perpendicular to the displacement, vertically down in this case. So where the cosine comes from, well, according to the angle here, the parallel side is the adjacent to the angle, and the hypotenuse of this triangle is the force. So if you write the cosine of that expression, or sorry, the cosine of that angle, adjacent over hypotenuse would be F parallel over F. And then when you solve for F parallel, it's F cos theta. So again, that theta is the angle between the force and the displacement. So the maximum amount of work is done when the force is parallel to the displacement. So the angle between, let's say a rocket is taking off, the force is pushing up and it is also moving up. So the angle between the force and the displacement, they're parallel to each other. The angle is 0 degrees. And if you take the cosine of 0 degrees, that's a maximum for the cosine function, it is 1. If there is, let's say you've got a person just holding a package, for example, on skis for some reason, there is no work done when the force is perpendicular to the displacement. So the student is exerting an upward force on the box. The box does not move upward at all. It only moves horizontally. So essentially, we're getting into questions, is work done or isn't work done when you exert a force over a displacement or whatever? Like you talked about that last year in Science 10. Basically, what we're going to get into is our emphasis this year is going to be more on energy transformation. So for example, does the box gain any height? Does it get higher off the ground? Does it gain potential energy? The answer is no. And if it's moving at a constant speed, it's not gaining any kinetic energy either. It's not getting faster. So since the box is not gaining any energy, no work has been done on it. Whereas the rocket taking off, when rockets take off, not only do they get higher, they gain gravitational potential energy, they also get faster as they move up. They accelerate, so they gain kinetic energy as well. And that's what we're going to get into today. Gravitational potential energy is the energy of an object due to its position above the surface of the Earth. Now, surface of the Earth is the reference point that we used mostly in Science 10 last year. However, EP equals mgh, there's a formula. Notice where it says h, height above reference. Now in Science 10, we just chose the reference to be the ground, where you choose the gravitational potential energy to be set to 0. But we're going to get a little bit more sophisticated in Physics 20, where the 0 level that you choose is completely arbitrary. It doesn't matter. So for example, here's a picture from your textbook of a textbook sitting on a shelf. If you choose, for example, the height to measure the potential energy with respect to the floor, mgh, you'd use height above the floor. If you choose your reference point to be the tabletop, it would be height above the tabletop. So with respect to the tabletop, it's got less potential energy than it is with respect to the floor. If you choose the height of the shelf itself to be 0, then it's got 0 joules of potential energy with respect to the shelf. If you choose the ceiling to be an arbitrary 0 level for potential energy, it's got negative potential energy with respect to the ceiling because it is below the ceiling. So it's kind of like, and it's not measuring energy, but the analogy I like to use is the Celsius scale. So 0 degrees Celsius, 0 doesn't mean nothing. It's not like temperature ceases to exist at 0. It just means that is an arbitrary, the freezing point of water is where nobody invited me to that meeting, but where it was picked for 0 degrees Celsius to be. So anything hotter than that's positive, anything colder than that is negative. Arbitrary. Same thing with the table here. If you choose your reference point to be the table in the picture, anything above the table would have positive potential energy with respect to the table, and anything below the table would have negative potential energy. In Science 10, we just chose the ground. So generally it's easier, or just to think about it where, well, why don't you just pick the lowest point in the room, the floor or the surface of the Earth or whatever, to be 0, and then everything above that is positive. And that's kind of like the absolute temperature scale or the Kelvin scale that you would have learned about in Chemistry 20, where you pick the coldest temperature that you could possibly get, minus 273.15 degrees Celsius, make that 0, and everything above that is positive. So an arbitrary reference point where you just set the gravitational potential energy to be 0. Kinetic energy. Kinetic energy is the energy due to the motion of the object. So an object has mass and it is moving at a speed v, it's got a kinetic energy given by the formula 1/2 mv squared, just like it was last year in Science 10. And that's it for today. Like, today's stuff is really short. You're not going to be asked to do really a lot of stuff this week. It's a lot of review. So section 6.1, read pages 292 to 298, skip some couple pages there, and then 302 to 303. Anything that's got to do with Hooke's law or springs or anything like that, omit that stuff. And there's some practice problems and a few check and reflect problems for you guys to try. That's it for today. Pretty short. See you next time.